Okay, so let's continue on with a few more questions. So I just need to make one little change for the last video. Was the last video should have been plus 137 kilojoules in number 8, not I think I said 131, 131.5. I think I must have just written too quickly and messed up, a 7 for a 2 or something along those lines. Because the value was close but not quite. So I wrote that in the description of the bottom of the last video, and also in this video if you're watching it. So your number should have been plus 137. So okay, let's move on to number 9. It's number 9 in your textbook. This is dealing with the bond enthalpy section. Bond enthalpy section. So what that means is that to calculate the bond enthalpy, our delta H of reaction is equal to the sum of the bonds that are broken, minus the sum of the bonds formed. So what this shows you, right? Bonds breaking is endothermic, and these are your reactants. And bonds forming is exothermic. So this is your products. So it's the bonds that are being formed in your products versus what's being broken in your reactants. So basically that's just your activation energy in order to break these bonds and make them, make an H2 break up into a reactive H atom. So let's look at the question. I've got it right here in front of me. So the question shows you a table, and this table is filled with numbers. So we've got an HH bond, we've got an FF bond, and we've got an HF bond. And our reaction that we're looking at is 2HF reacts to form H2 and F2. So basically we need to calculate the bond enthalpy for this reaction. So let's look at our reactants first. So if we look at the reactants, we have 2 hydrogen fluorine bonds. So 2 times, and the values here, which I forgot to fill in somehow, is 430, 155, and 565. So it's 2 times 565, and that's for reactants. And for products, we've got an HH bond, which is 430, and an FF bond, which is 150. So let's add these together. 430 plus 150 is 580. And if we do this math, 2 times 565, we get 1130. So we need 1130 kilojoules to break all the bonds, and we only release 580 joules or kilojoules. So that means that this is going to be an endothermic process. So let's look at our equation. Delta H of reaction is equal to bonds broken, which is 1130 kilojoules is how much we needed, minus bonds formed, which is 580. So our delta H of reaction is equal to 500, approximately 500, and oh, I messed up a number right here. This is 55, 85. I did this calculation before, so 585, and we end up with a value of 545 kilojoules for the delta H of reaction. So okay, so that's number 9, and let's go down to number 10. So number 10 is a bit of a little bit of a longer question. It's A, B, C. So we've got 10A. So 10 is, so it says the reaction between ethene which we draw like this, and hydrogen says is exothermic. Is exothermic. Exothermic. So 10A says write a reaction, or write the reaction for this. So if you remember from IGCSE, this is just a hydrogenation reaction. We're adding hydrogen to this double bond. Typically you need a catalyst, but we don't need to include the catalyst in this. So let's do C2H4 plus H2 reacts to form C2H6. And these are gases. Gas, gas, gas. So ethene is typically, it smells like camping fuel. So if you ever go camping, you know, you've got those little portable like camping gas tanks, and when you open up the valve, it heats your little burner, and you can make some coffee and stuff in the morning. So basically, ethene smells a lot like this camping fuel that we use. So okay, let's go to 10B. 10B, what's 10B? Deduce the stabilities. Deduce the stabilities of the reactants and the products. So how to deduce these stabilities? We just say, okay, it's exothermic. So if it's an exothermic reaction, it means that the bond strength in the products is greater than the bond strength of the reactants. The bond strength of the reactants. So what that means is that the products are more stable than the reactants. The products are more stable than the reactants. And then finally, let's talk about 10C. So for 10C, this is a bit more of a difficult one because this is a throwback to Unit 4. So it's continuing on. You need to remember Unit 4. Oh no, not Unit 4. So it's a throwback to Unit 4. So it says explain by referring to the bonds in the molecules, by referring to the bonds in the molecules. Why the reaction is exothermic? Why is the reaction exothermic? So this is, if we look at IGCSE or IB and IGCSE, we need to look at the keywords referring to the bonds. You must refer to the bonds or you get no points. So the first thing you want to do is draw the bonds, right? It's a logical thing, hopefully a logical thing. It tells you think about the bonds. You need to think about the bonds, so draw them out. What could it hurt? So if we look at ethene, we've got this molecule. We look at hydrogen, that's the molecule. And then we form ethane, so CC. Okay, so this is why this is a significant. This is why this is significant. Is you just need to consider right bonds. Like if we said a sigma bond versus a pi bond. So a sigma bond versus a pi bond, a single bond versus a double bond. So if we were to imagine these, we need to take into account both of these here. So I'm going to change my color. So if you remember, right, a double bond is stronger than a single bond. However, this is the thing is that a pi bond is weaker than a sigma bond. So right, a double bond is a sigma bond plus a pi bond. So a double bond equals a sigma plus a pi. But a sigma is stronger than a pi. So the sigma, the direct overlap. So right, if we were to draw out those orbitals, the direct overlap of these orbitals is stronger than this sideways overlap, right? We've got a carbon-carbon double bond. They've got a direct overlap in the center, and then they've got this sideways overlap above and below the axes, and these are your pi bonds. So a direct overlap is stronger than a side-to-side overlap, just based off of proximity. You can imagine it. So let's look at these molecules. We've got five sigma, 1 pi, 1 sigma, and here we've got 1, 2, 3, 4, 5, 6, 7. 7 sigma bonds. So here we've got 6 sigma in total plus 1 pi, and here we've got 7 sigma, and we know that sigma bonds are stronger than pi bonds. So if this has stronger bonds in it, it means that it's more stable. And if it's more stable, that means that that's why it's exothermic. That's why the reaction is exothermic. So that's the way you can describe it. How else can we think about this? Yeah, that's probably the best way. Honestly, this is the way I'd like you to explain it. Because this makes you remember Unit 4. If you forget Unit 4, we can't move on to Unit 5. So do not forget your Unit 4. Okay, so I'll continue on in the next video, because the next questions are very long, so I might just do one video per question, and we'll do number 11. I'll see you then.